The tool allows mapping SPAN models to XACDML models. SPAN models may be authored and exported in XML format with any SPAN-compliant tool such as EPF Composer and Rational Method Composer. We can then import the XML SPAN process in our tool. This is done from the File menu. The example used is a typical agile method for software development. The process has one phase named software production, consisted of several releases. Each release has the same structure. It includes a planning and development activity that starts with a release planning meeting where user stories are prepared to be implemented and ends with several iterations of development. During development, developers perform the pair programming with test-driven development task before the next planning and development activity. For instance, the pair programming with test-driven development is performed by the developer role. It has as input a user story that has been prepared during the release planning meeting. The task produces an implemented user story as output. At the end of the software production phase, a milestone named working software is reached. Now we are ready to start mapping this SPAN process model to a simulation model in XACDML. In this screen, you can see the graphical interface used to support algorithm number 1. The first algorithm maps SPAN roles to XACDML permanent entities and resource dead states. The resource dead states are implemented as queues in XACDML. The only configuration that we need to set here is type 4 for the number of developers in the project. The second mapping algorithm maps the SPAN work products to XACDML temporary entities, dead states, generate active states, and destroy active states. We follow the convention over configuration principle in order to mitigate the intervention of the simulation analyst during mapping. As can be seen, default values are used. In that sense, the time a simulation analyst spends during mapping of SPAN work products to XACDML elements is reduced. The only configuration we need to set for this recording is the initial dead state with 30 temporary entities, in our case, user stories. This screen allows to configure the parameters for algorithms numbers 3 and 4. The third algorithm is about mapping SPAN tasks to XACDML activities. The fourth algorithm maps SPAN hierarchical elements to XACDML dumb active states. A dumb active state does not advance the simulation clock when executed during a simulation run. We also use this interface to customize the generation of the XACDML model by providing quantitative data for several new attributes in extended XACDML. For each work breakdown element of the process on the left, we have the opportunity to configure the best fit distribution and estimated parameters for the duration of the element. The elements in the local view panel are automatically enabled or disabled based on the select work breakdown element in the left panel. Let's start with our first work breakdown element, the software production phase. For this element, I need to set process quantity to batch, and again refer to our paper to the meaning of each attribute presented in the extended XACDML panel. The next element is the release. Release is an iteration, a dumb active state within our approach. The time that we set and the best fit distribution parameters in these fields are the duration used for the time box fields. In our case, 14,400. I'm also gonna move processing quantity from unit to batch, and iteration behavior move back is okay. For planning and development, I'm gonna use a constant distribution with value of 10 days. They're used to set the time box attribute. I'm gonna change process quantity also to batch and condition to process to all entities available. Let's do release planning, a task with constant distribution of 1 business day, 480 minutes, process quantity, batch, and condition to process all entities available. Now we have an iteration, a dumb active state, with constant distribution, with a value of 4320, equivalent to 9 days. Processing quantity equals to batch, and condition to process all entities available. Now, pair programming with test-driven development. Here, our best fit distribution is a log normal with parameters of 1900 for scale and 1200 for shape. And the quantity of resources needed is equal to 2 in condition to process all entities available. And last, working software, a milestone with process quantity equals to batch. Now that we collected the parameters for all work breakdown elements, we are ready to generate the XACDML simulation model. When I click the Generate button, in addition to the execution of the mapping algorithms numbers 1 and 2, the algorithm number 5 is executed, generating the majority of the XACDML contents shown here. The 5th algorithm is a recursive one that correctly generates a pair of dumb active states, delimiting span activities, phase, and iterations. Its execution triggers the execution of the mapping algorithms numbers 3 and 4. The 4th algorithm allows generate dumb active states. As you can see, all the parameters collected in the previous screens are passed to the mapping algorithms and to the recursive one, and all these XACDML elements are generated automatically. Let's save our XACDML model. Now that we have an XACDML model, it is time to generate Java code from it using XSLT. By clicking the button, the tool executes behind the scenes the transformations from XACDML to Java. As you can see, Java code is generated from the XACDML model, and we now can use these Java codes to run our simulation and get the simulation results. I'm gonna save it. Now we are ready to execute the generate simulation model. In this graphical interface, we can specify the number of replications and whether the simulation run should end by simulation time or lack of temporary entities. The tool allows to determine which dead states are presented in the output results by selecting dependent as the variable type. I'm gonna set 36,000 here, roughly 75 days, or the simulation would end when no more user stories are available to be produced. And I'm gonna configure here with 10 replications. The results presented in the paper were averaged based on 200 simulations runs, but we configured here with only 10 to avoid pausing the video. I'm gonna click on Simulate. That's it. Now it is possible to see the simulation results. In our example, a snapshot at the end of each replication run with each dead state is printed in this text area component. Let me go to the beginning of the results. As you can see, now we have results grouped by replication. For example, in this first replication, the project duration took 52 days, and here is the snapshot at the end of the simulation run of the state of each dead state with user stories. As you can see, all the user stories at the end of this simulation run in the first replication are on Q6 and Q7. If you don't remember, I can come back a little bit, and Q6 and Q7 are the dead states mapped to the output dead states of the planning and development and end iteration dummy states. In other words, if a user story is located here or here, it means that it was implemented by the activity pair programming with test-driven development. Replication 3 to 64 days, but replication 4 55 days. And all user stories at Q7. At end of the simulation results, we can see the global results. On average of 10 simulation runs, it took 57 days to complete the project. And the user stories at the end of the simulation were at Q6 or Q7 with these values as you can see here. Thanks for watching.